Strategy for methods review. Here are my 5 ideas for how you could approach the methods review. Or if you're an author, keep in mind, this is how your paper might be reviewed by somebody who's thinking this way. There they are. I won't read them now because I'm going to go into each one in depth, but it goes from the easiest part of the beginning part all the way to the interpretation at the end. By the way, I'll also send you these slides if you're interested. All right, so name the design. So Andrew warned about using jargon, and I think he's right. Writing a lot of extra jargon in papers generally makes it harder for non-experts to read your paper. But there's a couple of exceptions to that. I think one of them is with the name of the study design. There's a piece of jargon that you could use to very efficiently communicate what type of study you did. Is this a case control study? Is this a retrospective cohort study? Is this a crossover clinical trial, et cetera? You get the idea. By using that piece of jargon, you're able to communicate quite a bit about what was done here. So as a reviewer, I try to ask authors to dig deep and come up with this jargon either in the title, abstract, or somewhere in the methods section. Again, by doing that, it allows me to access a lot of knowledge I might have about that type of design and helps me to review the paper better. As Andrew said really great, we need to know about the aims and the hypotheses. And then if I can know what the design is, I also know some inherent limitations to it. So if someone does a pre-post design, I've got 5 biases that I already know to watch out for. If someone's doing a time series study, well, I already have a couple biases to look out for there. So, but by naming the design, you can actually train yourself to be prepared for certain things to watch out for. And truth be told, they're finite, and you can actually learn these pretty quickly. And then the last part is that every single design usually lends itself pretty well to a type of analysis. If you're doing a clinical trial, you're usually doing very different types of statistical analyses than if you're doing an observational data analysis. Those are much more complicated than for a clinical trial. So by knowing what the design is, we can find the appropriate statistical analysis. Here's some common designs. In our world, the epidemiologists have won the day. The names they use for studies are the ones we all are using. That doesn't mean they're the only ones. If you looked at a different field, you'd see different names of designs, but there's some great examples there. As a quick reference, there's 2 books that I think are really fantastic. The one on the right, Experimental and Quasi-Experimental Designs for Research by Campbell and Stanley. This is a classic. 1965 it was written. It's been revised 4 times, but it still contains all of the most relevant designs, all the threats to those designs, so biases, confounds, things like that, and how they can be properly used to generate interpretations. The book is short. It's something like 60 pages. If you're looking for one desktop reference, this is the one I'd recommend. The Kirk book is also quite good, but it's from a statistical point of view. All right, last idea about the methods and the design point is if you knew the name of the design, if you knew this paper was a clinical trial or an observational study, then you could apply a reporting checklist to it. This would be like a handy aid to assist you in looking for the things you would need to know about this study. And lucky for us, the Equator Network, that's equator-network.org, is one-stop shopping. It's a group out of Oxford. And what they've done is they've collected all of the reporting guidelines for all different types of research. I think there's over 400 there now, different checklists that authors should do when they're reporting their studies. So if you're a new author, this is a great place to get started. If you're writing a clinical trial for the first time, you should look at the consort to see what elements of the consort need to be reported in your manuscript. If you're reviewing a clinical trial, yep, you should look at the consort to see what elements are there. Randomization, blinding, bias, things like that. So Equator Network's a good place to go. Of note is that in anesthesiology, we review every article for a relevant checklist. So if you submit to us an animal study, we're going to check it out for the ARRIVE guidelines. STROBE for observational research, STARD for diagnostic accuracy, and PRISMA for systematic review and meta-analyses. So as an author, if you had your manuscript ready to go with those things in mind, it's going to save you a lot of hassle on the back end. And as a reviewer, we sure could use the help to check these things out. So the Equator Network is a great place to go to find these checklists. All right, once you know the type of the design, now it's time to think about how were the variables measured? How are the ideas quantified? I'm thinking here about quantitative research. Every single construct needs to be mapped out into a number. That's just the way it works. And so how are these numbers done? Are they reliable and are they valid? This part of research we don't spend a lot of time thinking about, but it's crucially important. For example, if a clinical trial is using an outcome that the authors made up 2 minutes before doing the study, we don't know how reliable or valid that outcome is for measuring what we're looking at, or if it could be reproduced, or if there's a lot of noise in it. So reliability and validity of the measurements under study is really, really important. As a peer reviewer, I know I check all the measures to see, is there some comments about reliability? For animal studies, is a single rater marking histology? In systematic reviews, is it just one author who's looking at the evidence to see if it qualifies to be included in the study or not? Every step along the way is a chance for error, and peer reviewers, we have to check these things out. So by keeping an eye out for validity and reliability is really, really important. There's a couple of different measurement systems that we could use, but I think a real easy one to keep in mind is this nominal, ordinal, interval, and ratio. This comes to us from the social sciences from 1930s, but it works pretty well. The top one, nominal, is categorical data, and the bottom one, ratio, is basically ratio-scaled variables. As you go down the list, the data have more information in them. And if they have more information in them, they're more powerful. So if you're trying to design a study and you have to do a statistical power calculation, and you can pick between one of these types of measurements, you want to go down the list. As a reviewer, I have to be really careful, because if somebody does a t-test on ordinal data, that's inappropriate. T-tests require that the data are interval or higher. So if there's a 3-point ordinal scale and we're running a t-test on that, we violated the assumptions of a t-test, and I have to raise that as an issue. So as a reviewer, knowing the level of measurement of the variables allows you to check the statistical plan to see if it's appropriate. And as an author, it's good to know that so you can run the right tests. Anyway, I think this is really important to keep in mind. Okay, I was mentioned earlier about the reliability of a variable. So here's an interesting thing to think about. I talk about this a lot, and it usually goes over like a lead balloon. But the association between two variables, let's say you're correlating X and Y. Well, the maximum correlation between X and Y is only as high as their unreliability. So if we measure both with extreme amounts of error, we can't possibly find the two of them to be correlated. If we're looking at an odds ratio, so let's say we have an exposure variable on some outcome variable, and either the exposure or the outcome has a lot of error in it, well then the odds ratio is likely to be very close to 1, because error tends to diminish the associations we can possibly see. Here's an example of that. It's a complicated slide, but on the x-axis is the reliability of the predictor. A 0.8 reliability is generally considered pretty good. But you can see here that if the true association on that blue line was a 2.0, and the outcome was measured perfectly, it was perfectly reliable, we would still only see about a 1.85 odds ratio if the reliability of the predictor was 0.8. So we lose 0.15 odds ratio points because of unreliability. So oftentimes when we see investigators come to us with papers and they declare there are no differences here, we didn't see anything. There's no differences in the variables under study. One of the things to rule out as a reviewer is that everything is being measured unreliably. You don't need a reason to have no association if there's unreliability in the measures. So keeping in mind how things are measured and then keeping in mind the reliability helps you make this assessment. And by the way, the easy way to check that is just to see if you can see reliability coefficients, if you can see citations about the validity of the measurements, things like that. When in doubt, I just ask authors. I'll ask if this has been validated in the past or if they have any ideas about how reliable these measurements are. Okay, which brings me to the third point, the statistical analysis plan. This is something that's getting more and more attention because we now realize that one of the reasons why we're in a replication crisis is because statistical analysis plans are being formulated after authors look at the data, as Andrew was telling us about. Let me say something that may seem self-evident to you. Ready? If the analysis is conditional on the data, we're in trouble. The analysis has to be conditional on the hypothesis. You have to pick the analysis based on the hypothesis, run the analysis on the data, and then report the results. If the analysis gets reconfigured as you're running As you run the analysis, you look at it, you include some outliers, you run it again, you try cutting the data up in a different way. The more you do that, the less the inferences mean. The p-values don't mean what you think they do, the confidence intervals don't have the proper coverage, the whole thing defaults to noise. So we need to see a priori statistical plan wherever possible. If it wasn't possible, if it's a post hoc analysis, we need the authors to declare this fact. We need to know that. So the authors need to tell us which parts of their plan were developed before looking at the data, and which parts evolved after examination of the data. I read a paper last week, I thought it was really fun. The authors said that they had an a priori statistical plan, but it was the 5th analysis of these data. And I'm pretty sure this plan wasn't made 5 papers ago. So they had learned a lot about what they had seen on 4 papers, and on this 5th paper, this analysis couldn't possibly be considered to be a priori. It evolved after examination of the data. There's a way to do that, but it makes it much more complicated. Okay, and as a reviewer, I try to ask myself, could I replicate these analyses if given the data? That's the golden rule as a statistical reviewer. By reading your paper, can I replicate these analyses if you were to give me the data? If I can, you've given me enough detail. If I can't, then I probably need to know a little bit more. That's becoming a bit more gray now that analyses are becoming more and more complicated, particularly for observational research. But for a basic science study, it's still true. For a clinical trial, it's definitely still true. So check the statistical analysis plan to see if you could replicate the data. If you know a lot about statistical tests, you can start to think about the assumptions. Every test has a certain assumption that needs to be satisfied. Remember that example about ordinal data and t-tests? There's a great example. So if you know a lot about what the tests need to be valid, well, then you can start to check it on the fly. This is difficult because you usually need to know a lot about what the measurement is, what its measurement properties are, and how it's being applied. So that's it. But as a content expert, if you can help us with that, that'd be really, really great. Another error I tend to see a lot, and I think you'll probably see it too, is that some authors write the same statistical plan for every paper they do. It's got sort of a smorgasbord of tests. We ran t-tests, ANOVAs, we used regressions, and we tied them up with a chi-square. And by the time you get done, they pretty much tell you all the tests that they could have run in the paper, in the stats plan, but they don't actually run some of those tests. What we want is the actual stats plan that was in the paper. I mean, it's not too much to ask. So look for tests that were actually just introduced, but that actually are not in the paper. Okay, here's a pet peeve of mine that is unfortunately common, and I think one that you could catch. And this is the dichotomization, already the artificial dichotomization of a variable that is naturally continuous. Let's say you're predicting a dependent variable or an outcome, and that variable is measured continuously. It's a scaled variable. But a lot of times, what authors or investigators will do is they'll artificially dichotomize this variable. They'll put a cut point in it into high versus low, or they'll do a median split, low or above the median split. For clinical purposes, this kind of makes sense. You're thinking about, what about people who are high in this versus low? Can you predict high people? Responder analysis, you see this a lot in responder analysis. If you take a look at the change score, people who are high in the change versus low in the change. So why would you do this? Well, you can simplify the analysis. Can it simplify the interpretation? Well, yes and no, you'll see in a minute. Some people think that dichotomizing a variable makes it more reliable, and this is absolutely not true. By dichotomizing a variable, you're not making it more reliable. You're making it less powerful, but you're not making it more reliable. And then some authors will say an optimal cut point can be used. It can, but anytime you put an optimal cut point from these data, you make this analysis more sample dependent. It's much less likely to replicate in future samples. So you can find an optimal cut point, but it's difficult. So why wouldn't you do this? Look at the first one, loss of statistical power. If you artificially dichotomize your outcome, you might as well throw away 1/3 of your data. It goes back to the level of measurement. When you artificially dichotomize, now you have a variable that was ordinal or interval, and you're making it nominal. Nominal data don't have as much information in them. There's like 0 or 1, male or female, responder or not. So you lose 65% is efficient, you lose 1/3 of the data. You can't look at nonlinearity. And most importantly in this regard, you can't interpret scores near the cut point. If somebody falls 1 point below the cut point, they're in the low group. If they fall 1 point above the cut point, they're in the high group, even though they are separated by 2 points on a 100-point scale. And it's very difficult. So let me show you this visually, okay? So let's say we've got 2 groups of people, the red and the blue. The blue are the diseased group, and the red are the non-diseased group. And we've got a biomarker where we're trying to separate them. In the biomarker, we're trying to put a cut point in the biomarker. That's the green line below, at which point, if you have a higher score than this on the biomarker, you're in the diseased group. If you have a lower point, you're not. The blue and the red, the blue is shifted by about a half a standard deviation to the right. So it's just a little bit higher than the red. And you can see that green line. The y-axis of that by that green line is the probability of being blue, as opposed to the biomarker. There's no natural cut point there. If you put a cut point there, it would be completely arbitrary, and there's no natural place to go. Now look what happens if you go to 1 standard deviation. If the two groups are separated by 1 standard deviation, there's a little bit more of a cut point, but not much. Look at 2. Now if it's 2 standard deviations, maybe you can make an argument that right down the middle there, you can start to see plateaus on either side, but still there's some ambiguity, so gray area in the middle. Great news is if you've got 4 standard deviation separation, well now you can probably do it. But if you have 4 standard deviations of separation, you might as well apply for your Nobel Prize, because you don't see that very often in biomarkers. It usually means you know exactly what's going on. Okay, so artificially dichotomizing is a bad idea. As an author, you should try to avoid it. As a reviewer, you should try to catch it. Okay, reporting of results, my 4th one. Can you identify the size of the effects? As Andrew did a great job of beating up on p-values, we aren't looking just for p-values. P-values are a garnish. What we really want is the descriptive statistics. We want to know the actual data you observed. And what are the uncertainties around the findings? We want to see variability estimates, standard deviations, interquartile ranges, and of course we want confidence intervals for all the reasons that Andrew stated. So here's some common errors I think you could find as a reviewer. Look at the first one. I call this a solitary p-value. This is where the p-value is supposed to represent all you need to know in the sentence. Control value, p is less than, p is less than. There's no actual numbers in there other than a p-value. I don't know the sizes of the effects. I don't know the uncertainty in them. I just know that the authors think they differed statistically significantly. And for all the reasons Andrew stated, we don't know much in there. And this is not a good reporting style. If you see this, definitely make a comment as a reviewer. This is not okay. Let me beat up on basic scientists. Basic scientists seem to do this quite a bit. And they also seem to do it quite a bit in the abstract. And an abstract is where we need most amount of descriptive statistics, because if someone only reads the abstract, they need to see the size of the differences. All right, look at the second one, contrasting p-values. This one is pretty common as well. The treatment group was different than the baseline, significant p-value, but the control group was not. I believe this is encouraging me to look at the 2 p-values and say, well, the 1 p-value is significant, but the other p-value isn't, therefore the groups differ. That's implied here, and that is not correct. You cannot contrast p-values as evidence of a differential effect. You have to run a formal test comparing the 2 groups. So if you find this as a reviewer, please flag this. This is hard to see, but if you can find it, it's going to change the nature of the paper. The last one, of course, is that absence of evidence is not evidence of absence. If you fail to find superiority, you cannot declare equivalence. Just because we see a non-significant p-value doesn't mean that the 2 groups are the same. Oftentimes you'll see, the 2 groups did not differ, and you give them a p-value there. The best way to do that is to give the means and standard deviations of the 2 groups to show you that the 2 groups are actually, in fact, not different from each other. So catch those errors if you can. All right, interpretation. This goes without saying, but does the interpretation reflect the actual data? I don't know about you, but sometimes I read papers and I'm not sure exactly what the authors are commenting about, but it doesn't seem to be their data. I think the telltale for this is when the results section has references to other work rather than the current work. You can do that sometimes, but the interpretations have to be, of course, based on the current work. And you want to focus on significant findings while ignoring non-significant ones. If you see that, that's it. This is tough. So if the authors ran 100 different comparisons and they treated us with 5 of them, 95 are not important, 5 are significant, I think that's probably just error. But at the same point, that's what you see a lot in papers where they don't let us see all the inferences. They just tell us the ones they want us to see. If you knew what the study design was, you could actually see if the study design can support the interpretations. In observational research, you'll see the word prevalence and incidence quite a bit. But if the authors used convenience sampling, it's a stretch to say that you actually have the prevalence or the incidence from the population. It's convenient sampling. People who seek treatment are not the same as people in the general population. We have to be very clear about who we're talking about here. Okay. And as Evan and Andrew talked about, there's something called spin. So let me give you one of these before I close up here. Spin is specific reporting that can distort the interpretation. Isabelle Boutron has got a program of research that she's doing that is really fantastic, and she's done a number of studies. This is one of the first ones she did in 2010. And she's looking at is how often does spin occur in scientific research, clinical trials, basic science, et cetera. She's got some great discussions on it. I think I'll refer you to that, to her reference. She explains it much better than I do. But what is it? Well, it's a focus on statistically significant results rather than non-significant results. So again, if you ran 5 things, 1 was significant and 4 were not, a skeptical reader could focus on the other 4. Here's one, within group comparisons. This is one of my favorites. We've got Group A and Group B. Group A changes significantly, but Group B does not. Again, if you want to tell a difference between these two, you would have to compare A and B directly. You can't just say A is different than B because A changed and B did not. So a proper test of a differential effect using an interaction term or a different score or an ANCOVA would be a more appropriate approach. People tend to report to promote their secondary outcomes. So when the primary outcome doesn't go the way we wanted it to, the secondary outcomes all of a sudden seem a lot more important if one of them was statistically significant. So you tend to see the secondary outcomes get promoted in the abstract. They talk about these first. They're the ones they talk about in the conclusion section of the abstract. And it's like the primary outcome is less important. We can't allow that. Subgroup analyses. I love these in clinical trials, but I'm being sarcastic. I don't love these. The effect size worked. The primary outcome was negative, but it worked for women, but not for men. So on the fly, I did a subgroup analysis of males versus females. It worked for females, but not for males. That effect is likely to be so non-stable and likely to have been data-driven. You probably looked at a lot of different effects before you came up with that I suspect you would not replicate that effect. So subgroup analyses are difficult. And then the last one, that one's tough. If you don't see statistically significant results, they're not equivalent. So we try to show superiority between a new drug and an old drug. We failed to find superiority, but then we say, okay, but the two are the same, so that's great news, right? Well, the truth is we have to show equivalence before we can make that comparison. The last one's for just flat out fraud. There's been a few instances of that in the literature, but we haven't seen that in our journal, luckily for us. So how prevalent is spin? 61% of the articles that they looked at had spin. Look at that, beginning in the title. So the authors are trying to spin us beginning in the title, which is really interesting.